A couple of announcements. We have a quiz tomorrow. It will be at the end of the first hour. 2 problems from chapter 25 and the end of chapter 24. Okay. You have a homework due next Sunday night, and I advanced it so that you focus on the material on for the midterm. I also posted on Blackboard some review notes from the tutorials, okay, and also an old exam from King Fahd University of Petroleum and Minerals that covers the same chapters. So I want you to practice doing that exam on your own, and I will post later on the solution for the exam, or maybe a video recording of the solution. Okay, please, the minimum you have to do for the exam is, first of all, repeat the in-class examples on your own, all of the examples, including the conceptual questions. Second, repeat the homework problems and do them on your own. Do not look at the answers, do them on your own. Third, repeat the tutorial problems, not only the ones we do in class, but also the ones I post on Blackboard. This is the minimum. This is the minimum. The more you practice, the easier the exam will be. So the other sources of problems are the end of chapter problems in the textbook. So you have at every chapter, at the end of textbook, every section has a number of problems. So you can pick, for example, 2 problems from each section. Okay. The other excellent source of problem are the old KFU PM exam problems. For those, you have only the final solution. You don't have the steps. So you have to struggle to solve the problems. Okay. Again, the midterm will be easy if you solve many problems. Solve the problems, meaning without looking at the solution. Solve the problems. Make sure that you do the effort. Okay. So I will be available in my office hours and also in the hours before class, Tuesday, Wednesday, and Thursday in room 2011A. But if the time is not convenient, you can always contact me using Microsoft Teams or send me an email. We can connect and solve the problems or any questions you have. Okay, so let me remind you of what we have covered so far in this chapter. We have defined the average current. We said it's delta Q over delta T, and the instantaneous current is dQ dt. Okay. We also spoke about the microscopic model for the flow of free charges, and we said if we have the number of free charges per unit volume is given n, and the velocity or the drift velocity of the charges is related to the average current by this equation. The average current is n number of charges per unit volume times the Q. This is usually equal to E, because the free charges are usually electrons. Vd is the drift velocity times the cross-sectional area of the conductor. Okay. Then we expressed Ohm's law in a different way than you had before. We said the current density, which is current per unit area. So the current density is current per unit area, or the current divided by the cross-sectional area, is equal NQVD. We said the current density is related to the electric field. If you establish a voltage in a conductor, the voltage will create an electric field. Usually the electric field is delta V over the distance d. Okay. The current density is related to the electric field through the conductivity. So the current density is equal to conductivity times the electric field. We said the conductivity is the inverse of resistivity. Resistivity is rho and conductivity is sigma. Sorry, here, this is a mistake here. So here, rho is 1 over sigma. I forgot to correct this. Okay. So instead of writing J is equal conductivity times electric field, we can also write the electric field is the resistivity, rho times the current density. We also derived the fact that delta V is equal Ri. This is the Ohm's law that you're used to. Okay. And we determine that the resistance R is equal to the resistivity times the length of your conductor divided by the cross-sectional area, rho L over A. Okay, so it depends on the geometric shape of the conductor, and it depends on the resistivity, which is a property of the material. For example, nickel has different resistivity than copper, and so on. Okay, so today we'll hopefully we will finish the this material. And so let me go to where we stopped last time. Okay, so last time we did this example and we finished it, and we said the resistivity of the same conductor here is different depending on where you have the voltage. And we did the two cases, and we found out that we get totally different resistances based on where the voltage is applied across this conductor. Okay. Okay, the next question is, all right, so this I will not start the Kahoot for this one. Okay, assume you have a cylindrical wire that has a radius R and a length L. Okay, if both R and L are doubled, the radius is doubled and the length is doubled. Okay, does the resistance of the wire increase, decrease, or remain the same? Does. So if you double the radius and you double the length, what happens to the resistance? Does it increase, decrease, or remain the same? Okay, so think about it. 10 seconds. Okay, who says increases? Raise your hand. Increases. Raise your hand. Who says decreases? Okay. Who says stay the same, remains the same? Okay. So again, here I do not solve these questions just by thinking about them. I write down what's happening. We have the resistance R. Oops. Choose R is rho L over A, the resistivity times the length divided by the area, which is pi R squared. So this is R1. R2, now we double the length, it's the resistivity times 2L divided by pi, and the radius now is 2R, so this is 2R squared. Okay, so this is going to be equal, R2 is going to be R1 divided by 2. So clearly it decreases. It does not stay the same, because R is to the power 2 and L is to the power 1. So if you double L in the numerator and you double R in the denominator, R has a square, so that's why the denominator gets larger, so the resistance gets smaller. Okay, next problem. Okay, well, for this one I will start the Kahoot. And let me ask you, play, start. So join the Kahoot, because I want to make sure you understand this concept. Start. Okay. So the pin is 4840408. Join, please. Okay, so while everybody is joining, let me put the question. Okay, this is a question. So in the figure, as the applied voltage increases, so you have some material, we are showing the current versus delta V. Does the resistance of the diode, so this is a diode, a diode. The electrical engineers, they know a diode is like a valve. It allows current to pass at a certain voltage. Below that voltage, there is no current passing. Okay, so we want to determine does the resistance of the diode increase, decrease, or remain the same? A, B, or C? I'll give you 15 seconds. You can discuss. Huh? It's okay to discuss it. Ready? Ready? I will start the Kahoot. So I give you enough time, and you will have another 10 seconds. Okay. Wow, split. We have 12 that are correct and 13 that are incorrect. Okay. So here, what is the equation for resistance? We know the Ohm's law says delta V is equal Ri. That means R is delta V over I. Okay, so delta V over I. So it's it's the inverse of the slope. This slope here is delta I over delta V. Let me write it delta I over delta V. Okay, so this is actually 1 over the slope. You can see that the resistance of the diode, the slope increases. Since the slope increases, the resistance has to decrease. So the resistance decreases. So because the slope is increasing, and since the slope is in the denominator, that means the resistance has to decrease. Okay. In electrical engineering, sometimes instead of plotting I versus delta V, they plot the opposite. They plot delta V versus the current I. In that case, whatever the curve is, in that case the slope is equal to R. So they call it IV characteristic curve. And some people plot delta V versus I, and some people plot the opposite. So you have to be careful. Okay, next problem. Okay, we have a radius of a 22 gauge nichrome wire is 0.32 millimeters. Calculate the resistance per unit length. Resistance per unit length of this wire. So, resistance per unit length. We know resistance is rho L over A, and we divide by L. So L's will cancel. So this is going to be the resistivity divided by the area, and we have resistivity is given. Nichrome wire, the resistivity is 1 10 minus 6 1. Yeah. Okay. I found the trick. You just have to press in the back of the. Okay. 1 10 to the minus 6 ohm meters divided by the area. So we are given the radius. So this is pi r squared, and r is 0.32 10 to the minus 3 squared. So this is the resistance per unit length. The number here is 3.1 ohms per meter. So this is 3.1 ohms per meter. Okay, the next question. If a potential difference of 10 volts is maintained across 1 meter length of the nichrome wire, what is the current in the wire? So we're given the length here, okay, and we're given the potential difference of 10 volts, okay, and we are asked to determine the current in the wire. Well, from Ohm's law, we know the current is delta V over R, okay, and so this is delta V, we know. R is rho L over A. So we have rho over A is 31 ohms. We multiply it by 1 meter. So this is going to be equal to 10 volts divided by the resistivity, which is 1 10 to the minus, we already have resistivity divided by area. We already have the value, 3.1 ohms per meter, and we multiply it by the length of 1 meter. Okay, so we get 10 divided by 3.1, which is 3.2 amps. So this is 3.2 amps. Easy, eh? So we have Ohm's law, delta V is equal Ri, and the equation for resistance R is rho L over A. Okay, next problem. This is a more challenging problem. Okay, we have a coaxial cable consists of two concentric cylindrical conductors. So there is an inner conductor of radius A and an outer conductor of radius B. The region between the conductors is completely filled with polyethylene plastic, as shown in the figure. So the green color here is the plastic, polyethylene plastic. The cable is designed to conduct current along its length, but that is not the current being considered here. Yani normally the conductor that is inside, that's where we conduct the current, and usually the outer conductor we connect it to ground for shielding and so on, and reducing the noise. The problem here is that's not the current that we are interested in. We are interested in what we call the leakage current. Okay, the radius of the inner conductor is 0.5 centimeters. The radius of the outer conductor is 1.75 centimeters, and the length is 15 centimeters. Okay, the resistivity of the plastic is 10 to the power 13 ohm meter. It's a very high resistivity because it's not supposed to conduct. Calculate the radial resistance of the plastic between the two conductors. The radial resistance. So here we are interested in the resistance between the inner conductor. Let me draw the resistor as if it's here. So we're interested in this resistance between the outer conductor and the inner conductor. Okay? Now, so far we have an equation. We said the resistance is rho L over A. But, okay, so here the L is actually not L. It's L, in this case, the length is going to be here, B minus A, because that's, and the area, we can consider the area is the belt of the cylinder. So instead of using this equation, we're going to use, let's take an element, this element here, in the plastic of radius R, small r, okay, and of thickness dr, and we want to determine what would be the resistance of this element. So I will write it dr because it's just an element. Okay, so let's use the resistivity times the area. What's the area in this case? The area of the belt of the cylinder is the circumference 2 pi r times L. So L, sorry, this is dr. The L is dr. It's this thickness. This is dr. This is L. Okay, so we'll call it dr. What is the area? The area is the area of the cylinder. So it has a circumference of 2 pi r. Okay, and the length of L. So it's 2 pi r, which is the circumference, times L. This is the element resistance of this element. Now, if I want to determine the resistance from A to B, I can integrate this. So the total resistance is the sum of all of these dRs when dr goes to 0, which is the integral of dr. So this is the integral. Let's take the constants outside the integral. It's rho divided by 2 pi L, the integral of 1 over r dr, and we're going from A to B. From A to B. What's the integral of 1 over r? Log of r. So this is going to be equal rho divided by 2 pi L log of B minus log of A, which is log of B over A. So this is the equation, and we can replace the numbers. Okay, so rho over 2 pi L log of B over A, and if you enter the numbers, you find the resistance of this plastic is 1.33 10 to the power 13 ohms. Very big resistance. It's 10 to the power 12 is, well, 10 to the power 9 is giga. 10 to the power 12 is what? Forgot. Huh? But anyway, it's a very big resistance, and it's supposed to be like that. It's not supposed to conduct current. But unfortunately, sometimes we have a leakage current, and usually we want to avoid that. Okay? Because it will cause noise in our signal. Okay? The next thing, I want to go to presentation mode for the next part. Whenever I try to switch the mode, it slows down my my computer here. Duplicate slideshow. Okay. All right. So now let's go to the next slide. Okay. We already spoken about the Paul-Drude model. We said when you have a conductor in electrostatic equilibrium, the electrons, the free electrons, are moving randomly, so the net movement is really zero, and they have zero average velocity. But once you establish the electric field, you put a voltage and you have an electric field, the electrons start, the free electrons, they will be exerting, they will experience a force opposite to the direction of the electric field, and they will drift with a velocity Vd that we have determined early on. Okay? We want to develop this further. We want to determine the force. We know the force, the electrostatic force, is Q times E, okay? And the charge Q is that of an electron, it's minus E, okay? And we can write Newton's second law. This force, we assume this is the only force acting on the electrons, because the gravitational force is negligible compared to the electrostatic force. So we can write Newton's law, A, the acceleration, or the sum of the forces, is equal to ma. We can determine the acceleration. In this case, the only force is the electrostatic force, so it's QE divided by the mass of the electron. Now that we know the acceleration, we can try to determine what is the drift speed. We can try to determine the drift speed if we assume the equations of motion with constant acceleration. You have seen in physics 121, if you have only a constant force, you have constant acceleration, and you can use equations of motion at constant acceleration. This is what we will do. Okay? So this is the equation, one of the equations of motion. The final velocity is equal to the initial velocity plus the acceleration times t. So we're writing this equation in vector form. Okay? The initial velocity, the acceleration we determined, it's q e divided by the mass of the electron times t. All right? We said initially the free electrons, they have a zero average velocity because they are moving in all directions randomly, so they have a zero initial velocity, and that's what we will assume. So we assume the average velocity of the randomly moving electrons is zero, and now we can rewrite the equation. So the final velocity, the average of the final velocity, which is Vd, is equal, so if this element is equal to zero, it's equal to QE, charge of the electron, times the electric field divided by the mass of the electron times the time t. And now we're using tau instead of t because we are interested to determine what is the average velocity between collisions of the electrons, between one collision and the next collision. We're calling this time it takes between collisions to be tau, and that's what we're remember previously we said the current density is current per unit area, which is NQ times Vd. All right, so we're going to use that, and we're going to write. So since I have this equation now for Vd, I'm going to put it here, okay, and write the equation for the current density. So notice it has Q, and the equation here has another Q, so you will have NQ squared times the electric field, the magnitude of the electric field, divided by the mass of the electron, times the time between collisions, tau, So tau is the average time interval between collisions. Okay, so now we have another equation for the current density, but in this case it's not as a function of well, we replaced Vd by this expression. We replaced Vd by this expression. Okay, let's take it further. The average current is the current density times the area, the cross-sectional area. So if I use the equation that I had before, this becomes nq squared times the electric field divided by the mass of the electron times the average time between collisions times the cross-sectional area of this conductor. This is the average equation. Okay? Since Ohm's law that we have seen says that the current density is equal to the conductivity times the electric field, okay? And we have the equation now for a new equation for the current density. We can have an expression of the conductivity. So this now is just equal to the conductivity because of this. So now we have an expression of the conductivity of a material. It's equal n times q squared, the charge of the free electrons, squared, times tau, the time between collisions in this material, divided by the mass of the electron. So if you give me a material and you give me the number of free charges in that material per unit volume, and you give me also how much it takes for an electron between collisions, I can determine what is the conductivity, and 1 over conductivity is the resistivity. So I can divide or inverse this to get the resistivity. So the resistivity is equal to the mass of the electron divided by n, the number of free electrons per unit volume, times q squared times tau, the time between collisions. So this is, okay, and remember, the number of free charges and the time between collisions is a property of the material. So different materials, the organization of the atoms or the molecules in the different materials are different. So the time the electron will spend between collisions is going to be different depending on the matrix of the atoms or the molecules, and also depends on how many free electrons are available in that material. Okay? So finally, we can write the average time between collisions is related to the average distance between collisions, which is usually referred to as the mean free path, L average, and the average drift speed, V average. So we can write that the average time between collisions is equal to the average, the mean free path, or the average distance between collisions divided by V average. This is so. This Drude model is really a microscopic model that completes the picture. Previously, you had only V is equal Ri, and you did not understand what is going on inside the conductor. What is happening to the electrons, how they're moving, how much the speed they have, how much they travel between one atom to another, and so on. So now you have a different or microscopic picture about what is really happening. Okay. Now, the resistivity of the material is not constant. It varies with temperature. We said different materials have different resistivity. Unfortunately, this resistivity is not constant. If you increase the temperature of a material, the resistivity will increase. Well, the resistivity, yes, the resistance will increase. Yes, the resistivity will increase. Okay? And the equation we have is a new equation. It says the resistivity at a certain temperature T, this is in Kelvin, is equal to the resistivity at an initial temperature T0. Usually we take it to be room temperature, but not necessarily, okay? Times 1 plus alpha T minus T0. Alpha is what we call the temperature coefficient of resistivity. Temperature coefficient of resistivity, okay? This is different from one material to another. And T minus T0 is the final temperature minus the initial temperature. Okay? So usually we measure the resistivity rho 0 at room temperature. But if we have the conductor is heating up and the temperature increases, for example, to 200 degrees centigrade, the resistivity or the resistance of the material will not remain the same. It will change with temperature, and we have to account for that. Okay, so since R is equal rho L over A, and let's assume for this argument, for this, that L and A are not changing, or they change in a very small fashion. The length of the conductor and its cross-sectional area, they change, but they cancel each other. Huh? Let's assume that, or the change of the length and the cross-sectional area is negligible. Okay, so that means we can write the same equation also for resistance. Okay, because if I multiply by L over A here, and I multiply by L over A here, I get R is equal R0, which is resistance at nominal temperature, times 1 plus alpha T minus T0. I told you the temperature is in Kelvin, but does it matter? T minus T0, if from Kelvin to Celsius, is it the same or different? Same. Delta T, if it's in degrees centigrade, if you go, for example, from 20 to 50, so if you go from 20 degrees centigrade to 50 degrees centigrade, delta T is 50 minus 20, that's 30, so delta T is 30. Let's now convert this to Kelvin. 0 degrees Kelvin is what? 273 approximately. Yeah? So 20 degrees, that's 273 plus 20, that's 293 Kelvin. Okay? When we go to 50 degrees, if we convert 50 degrees, so 50 plus 273, that is 323. صح? 273 plus 50, yes, 323 Kelvin. What's delta temperature? It's 50. So delta T in Celsius and Kelvin are the same. So you don't have to worry, is it Kelvin or is it centigrade? But in some equations, sorry, 30. Did we say, oh yeah, here 30. So we went from, okay, so 50, yeah, so 30, thank you. Okay, so in some equations you have to be careful. Like for example, PV is equal nRT. I'm sure you have seen this in chemistry. In this case, you have to use T in Kelvin. You don't use T in degrees centigrade because they are different. Okay, so whenever you have delta T, you don't have to worry whether it's Kelvin or centigrade. But if you have just T, then you have to be very careful. Okay, so the next equation. This is the temperature coefficient. It's equal the change of resistivity per divided by the initial resistivity divided by delta T. Usually alpha is given in a table like this. So for example, you can see different materials, they have different resistivity and different temperature coefficient. So these two parameters are property of the material. Okay, so copper, for example, has a very low resistivity and has a temperature coefficient of 4.3 10 minus 3. Okay, if we take well, it's interesting. Silver has a lower resistivity than copper. Gold also, but no, gold has a higher resistivity. Obviously, you cannot make your wires in silver. That will be very, very expensive. Okay, so the next equation is if we apply it to resistance, we get the same equation. R is equal R0 times 1 plus alpha T minus T0. So the resistance of a material changes with temperature. And if we plot this, this is what we get. If we plot the resistivity versus temperature, and in this case it's in Kelvin. Okay, so this is 0 Kelvin, at 0 Kelvin. So for materials like copper, the resistivity is nearly proportional to the temperature. So you can see that this is almost a straight line, but not really. You can see in this region it becomes a little bit non-linear. Okay, so it almost changes linearly with the temperature in Kelvin, except at very low temperature. And in fact, when you go to very low temperature, this is a magnification of this figure. Okay, you can see that it is really non-linear. And so the non-linear region exists at very low temperature. Usually we are not operating at 0 Kelvin. we're usually operating at room temperature, which is 293 approximately temperature, Kelvin. Resistivity usually reaches some finite value at the 0 Kelvin, at the absolute zero. Absolute zero is 0 Kelvin, which is minus 273 approximately degrees centigrade. Okay, but people who are working with superconductivity or superconductors, they bring the temperature quite low, okay, and the resistance becomes so low that it's almost zero. Superconductors, their property is they almost have zero resistance to current, which makes them very useful. You can pass very high current through these materials when you cool them. For example, when you go in the magnetic resonance imaging machine, they use a very high magnetic field, about 3 Tesla. In order to generate this very high magnetic field, the coils that they have that generate this magnetic field, they have to be cooled so that they become superconducting. And they pass a very high current through them because they have very low resistance or almost zero resistance, and then they can generate a very strong magnetic field. Okay, so this is an aside. Okay, next checkpoint. Let's go back to Kahoot. Come back to the Kahoot and let's go to the next one. All right, next. Okay, so 59174 is leading, or she is leading. Okay, all right. So when does an incandescent light bulb or a tungsten light bulb carry more current? Immediately after it is turned on and the glow of the metal filament is increasing, or after it has been on for a few milliseconds and the glow is steady. I'll give you 15 seconds to think about it, 20 seconds. Think about it and discuss it. Think, pair, and compare. Think, pair, and compare. You can think, pair, and compare with your neighbor. And let's see if that improves the results. So when you turn on the light bulb, is the current highest when you just turn it on, or later when the light is now constant? This you can think about it from everyday experience. From everyday experience, you should be able to answer this question. Okay, so ready everybody? Okay, next. So you have only 2 choices here, A and B, so don't put C or D. So you have only A and B. 5 seconds. Exactly. So we have 17 correct, we have 7 incorrect, and still we have 2 are lost. They think it's all right. All right. Now, when does a light bulb blow off? Have you ever seen a light bulb blow off after it has? Usually, when you turn it on, sometimes you turn it on, immediately it burns. The current is highest at that time. Why? Okay, if you draw. So let's say this is the resistivity, and we said, so let's assume when you turn it on, you're at room temperature, T0, okay? At room temperature, originally the light bulb was at room temperature, okay? Then, after some time, it's now burning, the temperature would have increased. So the resistivity increases. If the resistivity increases, that means the resistance also increases, okay? And what do we have? We have delta V is equal Ri, or I is delta V divided by R. So which current is highest? This current here at this level. So since R increases, that means the current will decrease. So here the current I2 is going to be less than the current at I0. That's why the light bulbs, many light bulbs, the old ones, as soon as you turn it on, it blows. In the house I'm renting, I'm having a problem with my light bulbs. And I keep changing them, okay? And the landlord told me from the beginning, look, you are responsible for the light bulbs. And then I understand why he said that, because I have to use more expensive light bulbs. Okay, so from everyday experience, you can see that in your own homes. Okay, next problem. A light bulb has a tungsten filament and is powered by a battery. When the bulb is turned on, it's just turned on, its temperature is almost room temperature, 20 degrees centigrade, and the current passing through it is 0.85 amps. This is right at the beginning. After 60 seconds, so now it has warmed up, the current is 0.22 amps. You can see the current has gone down. What then is the temperature of the filament? We want to determine the temperature of the filament. Okay, so we have an equation that says R is equal R0 times 1 plus alpha T minus T0. Okay, we are given T0 and we are asked to determine T. We are given alpha, okay, but notice we are not given R and R0. We are just given the current. Okay, well, I know R is equal delta V over I. So I have two values of R. We have R delta V over I, and we have R0 is delta V over I0. Correct? So I'm going to write that here. So R is delta V over I here. This is the second current. The initial current, the R0 is now delta V divided by I0. This is the initial current of 0.85 amps is equal to 1 plus alpha T minus T0. Okay, so the nice thing here, delta V cancels, and I have, so I can rewrite this. So this is going to be I0 over I minus 1 is equal alpha T minus T0. So I can solve for T. T is going to be 1 over alpha I0 divided by I minus 1 plus T0. Okay, and if I want to calculate that in degrees centigrade, I can do that, or in kelvins, I can do that. So let me use degrees centigrade. So this is going to be 1 over alpha. It's 1 over 4.5 10 to the minus 3. I0 is 0.85 divided by I, which is 0.22, minus 1, okay, and plus 20 degrees centigrade. So when you do that, you find that the temperature is 656 degrees centigrade. Okay, and if you're asked for Kelvin, you can convert that to Kelvin. You just have to add 273 to get the degrees in Kelvin. So this is very important equation, and you can see problems sometimes combining the temperature effect and other aspects of the Ohm's law, or the rho is equal R is equal rho L over A, and so on. So you have problems that can use more than one concept at the same time. The last concept we want to cover is the power. Okay, and let me, okay. We go to presentation mode again. Okay, so you can see there, if you have a battery and you connect a device to it, and let's assume you know the voltage across it, you have a multimeter, you measure the voltage and you measure the current. If you have the voltage and the current, you can determine the power through that device. The equation for power is, you have seen this before, is IV, but here we're using delta V, so it's the power which is the rate of electric energy transfer from the battery to the device, is equal I times delta V. This is for any device, whether it's an engine, whether it's a capacitor, whether it's a resistor. It's the same equation. This is very general equation. Okay? If the device is a resistor, we have an equation that relates I and V and delta V. Delta V is equal to Ri, which is Ohm's law. So we can exploit this. So I can replace, for example, delta V by Ri. You obtain the power is also equal to Ri squared. Or I can replace the current by delta V over R, and the power becomes equal to delta V squared over R. So you have three equations. If it's a resistor, you have three equations. Either delta V times I, that will give you the power, if you have the voltage and current. If you have the current and resistor, you use Ri squared. Okay? If you have the voltage and the resistance, you can use delta V squared over R. So you have three equations that are equal or equivalent that you can use if it's a resistor. This is because it's Ohm's law. This is, you can do that because delta V is equal to Ri. But if you take a capacitor, the power through the capacitor, so the power through the capacitor is going to be I times delta V. This is the power through capacitor. And remember, for the capacitor, we have seen Q is equal to C delta V. So you can write, this is I, delta V is Q over C. Q over C. So you can you can determine if you have the charge, the current, okay, so here this is also going to be I. Remember we said I is dq dt times Q over C. Okay, so you can do that, and we will do that in a future chapter. Actually, we'll deal with capacitors, charging and discharging capacitors. Okay. So if you have a motor, for example, and you know what's the current that is flowing through the motor, and you know what's the voltage difference, you can determine the power. Remember, power is energy per unit time. So the power is energy in joules per unit time in seconds. And the unit for power is watt. 1 watt is 1 joule per second. So here, the capacitor, if you have the current and the potential difference, you can, the rate or the power is I delta V to charge a capacitor. Okay, the electric energy from the battery is transferred to the resistor as heat. So that's why when you connect the resistor to a battery and you touch the resistor later, you find it's warm, because this energy is dissipated as heat. It causes the molecules of the resistance or in this material to vibrate more, okay, and when they vibrate at a higher velocity or more, the internal energy is increased, so it's dissipated as heat. Okay, so the electrons drift through the resistor, they collide with the molecules of the resistor. This increases the random motion of the molecules, that are constituting this conductor, okay, which is equivalent to higher temperature. Okay, unfortunately you did not cover thermodynamics. Hopefully you will cover thermodynamics, especially those who are in mechanical engineering or chemical engineering. You take thermodynamics course, and that's very important physics. Okay, so here we just will go quickly through the derivation of this. The rate at which electric potential energy of a system decreases as charge passes through a resistor is given by du dt. Okay, we have 1 more minute, and U is Q delta V. The potential energy is Q times delta V, so we can write this as dq dt times delta V, because delta V does not change with temperature, with time, sorry. And so dq dt is the instantaneous current, so it's I delta V. So we can get, this is actually the power, is equal I delta V. So actually, when the current passes through the resistor, so P is equal I delta V, okay, the potential energy decreases because it's dissipated through the resistor. But when it goes back, the electrons or the charges, they flow through the battery, they gain again their potential energy through the chemical reaction that is happening in the battery. So energy is generated by the battery and it's consumed by the resistor. Okay, and so you take the energy that is added to the system minus the energy that is lost. If you take this as a closed system, including the heat and so on, normally the energy is conserved. But actually, the heat is lost, and so part of the energy of this battery is lost to the outside world. Okay, so the power is I delta V. Remember this for any device, and these three equations for a resistor. I will stop here. Tomorrow we'll solve problems from this chapter, and we might start solving general problems from other chapters too. Okay, well, we don't have time to have a quiz. Okay, so the quiz will be at the end of the first hour, so the students who have a class can join their classes. But please, I see many students leaving in the middle of the class, and I don't know why. Okay, and I really don't want to take time to ask them. I don't want to harass them, to embarrass them, not harass, embarrass them, but I don't want to lose time of my lecture. Please, if you do not have something urgent, do not leave the classroom, okay? Because this is important. Okay, we'll see you tomorrow.